In our other gas law videos, we were typically dealing with 2 or maybe even 3 variables. I've written those gas laws out to the left side so you can see them. We had Boyle's law from when we were dealing with just pressure and volume, Charles' law when working with volume and temperature, Gay-Lussac's law, which I didn't have a video on, but you can also use if you're dealing with just pressure and temperature, and then your combined gas law for when you're working with those 3 variables, pressure, volume, and temperature. So what happens when we want to deal with even more than that? So those are all great and very important when describing gases, but we can also talk about the number of moles present. So if you want to talk about the number of moles present in a sample, then you would have to use this little lowercase n right here. That n is the number of moles. And that formula right there, this PV equals nRT, this is what we call the ideal gas law. So you can relate those 4 different variables to describe gases. You can talk about pressure, volume, the number of moles, and temperature. So you may be wondering what this capital R is right there in that equation. That R is a constant. It is the ideal gas constant. And I took this big, long explanation straight from your reference sheet, so you have that available to you. Notice that there's 3 different versions of that letter R, of that constant. We have the 0.0821, 8.31, and 62.4. So it does not mean that there's 3 different constants. It just means that you use the different constants when working with different units. So for example, in the first one, notice we have liters times ATM, that atmospheres, over moles times K. That is typically what you're going to be using. That's what you've been using so far when working with your gases, is measuring that pressure in atmospheres, the volume in liters, your moles, obviously measuring that in moles, and then your temperature in Kelvin. Notice all 3 of those have liters, moles, and Kelvin. The only thing that differs is how they're measuring that pressure. So the second one is if you're dealing with kilopascals, and the third is if you're dealing with millimeters of mercury. So you can use any of these 3 R constants, or if you want to, you can just change your pressure into ATM, atmospheres, and just use that first one. We also discussed standard temperature and pressure. So that is when you have 0 degrees Celsius and 1 atmosphere. So that only works under that standard temperature and pressure. You'll have practice problems that'll say, given standard temperature and pressure, what is the, whatever variable you're looking for. I also want to point out that if you have standard temperature and pressure, if it is 0 degrees Celsius and you are at 1 atmosphere for your pressure, then your volume of an ideal gas would be 22.4 liters per mole. We didn't discuss this before simply because we weren't yet dealing with moles, but you may come across situations when using the ideal gas law when you're talking about something at standard temperature and pressure, or at STP. So let's look at a practice problem. So this says 2.3 moles of helium gas are at a pressure of 1.70 atm, and the temperature is 41 degrees Celsius, and we want to know the volume of the gas. So I pulled out those variables just like I did in previous examples, and I simply just wrote it out in the order that I would be doing the problem. So PV equals nRT. I wrote out P, that's 1.70 atmospheres. Volume we don't know yet. And then N is over here, 2.30 moles. And then R is our constant. I wrote it out at the bottom. And T, which I converted from Celsius to Kelvin. Notice for the R, we are using the one that has atmospheres because that is the pressure that we are working with, is 1.70 atmospheres. So if PV equals nRT, we want to make sure that V ends up on a side by itself since that's what we're solving for. So divide everything by P. And now we are working with V is equal to nRT over P. At that point, we just plug in our numbers. We have N, which is our moles. We have R, that's our constant. And T, that's our temperature in Kelvin, over that pressure in atmospheres. Now notice something here. We have moles at the top here, moles at the bottom of our R. Kelvin at the top here, Kelvin at the bottom of R. And then atmospheres at the bottom, and then atmospheres and our R value. So all we are left with is this liters that is in that R value. That's why it has so many units and looks kind of convoluted, is because they will all cancel out except for the one that you are solving for. So in this case, we get our volume to equal 34.9 liters. Notice if you are working in problems in the future that don't involve moles, that are only comparing pressure, volume, temperature, any 2 or 3 of those, you do not need to use the ideal gas law. You can still use Boyle's law, Charles' law, Gay-Lussac's law, or the combined gas laws. This is only when you have 3 different things and you're solving for the 4th value. So if you have pressure, volume, and moles, and you want temperature, then you would use this sort of equation. So just keep that in mind, that you're picking the correct formula depending on the problem you're